I also ought to explain that tonight, this format is the first time we've tried anything like this, so we hope it's going to work okay, and we hope you're going to enjoy it, because it's going to be slightly different from a normal formal presentation. What we're going to do is have a conversation with me hopefully doing the leading of the conversation with two of our MacRobert winners who will intersperse their answers with slides and video clips to try and put the whole story together. So rather than just a formal presentation and then a Q&A after it, we're going to try and run it as a conversation piece, and then after a certain time in the conversation we'll open it up to questions from the floor. And if you do ask questions, please, can I ask you if you would mind standing or at least waiting for the microphone, saying who you are before you actually speak, so that that's picked up by the TV lead as well. So it falls to me just to do a bit of introduction. I mean, the MacRobert Award is widely regarded as the most coveted in the industry. Many would describe it as the Oscars of engineering. Because it's known for the next best thing in the technology sector. It identifies outstanding innovation with proven commercial success and tangible social benefits. These are the three driving elements of the MacRobert Award. And as well as gaining the prestige from the award, the winners actually receive a gold medal and a cash prize of £50,000. And the award is given to them as individuals, not to the company that they represent, although what they do with it afterwards is entirely up to them. It was originally founded by the MacRobert Trust, and I'm delighted that MacRobert are continuing their support by jointly hosting the event this evening. And I'd also like to thank the award's newest supporters, the Worshipful Company of Engineers, who've also helped enormously with the continuing success of the MacRobert Award, and are also sponsoring the evening tonight along with the Trust. Now, previous winners of the award include EMI, and in 1972 they developed the CT scanner, and so we awarded the MacRobert Prize 7 years before Sir Godfrey Hounsfield actually received his Nobel Prize for the invention, so we were ahead of the game with that one. Other notable winners include Rolls-Royce for their Trent engine, which is still flying many of us around today. And then more recently, Touch Bionics in 2008 for their iLimb bionic hand, demonstrating the wide variety of technologies that come before us as a MacRobert committee. And then in 1999, there was the MacRobert Award for the iconic Millennium Dome, and one of the winning team members for that was Paul Westbury, who was the youngest ever winner of the MacRobert Award. He was only 28 at the time that he won. But I'm pleased to introduce our guest speakers for this event, who are Professor Wyn Rampen and Dr. Neil Caldwell from Artemis Intelligent Power. And Artemis won this year's award for their pioneering digital displacement power system. It's digitally controlled hydraulics that has the potential to transform the viability of offshore wind power and low carbon transportation and many other applications. But before they actually come up to the stage and we start the conversation, what I'd like to do is just play for you the award video that was shown at the Royal Academy of Engineering's award ceremony back in July, just to give you a taste of what's to come. So if we can play the video, please, that would be great.
Artemis Intelligent Power was a company that we spun out of the University of Edinburgh in 1994. There were a lot of renewable energy projects on the go and no realistic way of matching the movements that natural forces bring to the movement that a generator that makes electricity requires.
Digital displacement technology replaces the conventional analog mechanisms of hydraulic machines with a completely digital control method. Each working chamber of the machine is provided with a solenoid-controlled valve, which is controlled by an embedded computer which is synchronized to the rotation of the shaft. every working stroke of our machine is controlled in real time by a computer.
Of course, this technology didn't exist. It was really by making first small demonstrator machines and understanding what the technology can do that we realized how big the potential is.
For the first wind applications, we wanted to do something big straight away. And so we were looking at several megawatts right from the very beginning, using a ring cam pump. And you're choosing what fraction of the pumping modules you want to deliver the power. So you've got variable speed input and absolutely fixed phase frequency output.
One of the most impressive aspects of the technology is really the way it's designed. So the 7 megawatt transmission is made of many modules of the same, say 100 kilowatt. And if anything happens to any of these modules, they can simply be disabled and everything else continues working.
I think the very exciting thing about digital displacement technology is that it can be applied to so many different markets, and apart from the environmental benefits from this technology, it brings employment. It's great in a way to see that it is possible in the UK to build a company that can develop but also manufacture and enter into world markets.
Okay, so that's a starter for 10 and a taster for the rest of the evening. So if Neil and Wynne can come up and join me on the stage. Okay, so if we go right back to the beginning of your story back in the early 1990s, Wynne, nobody had ever actually built a giant wind turbine. What made you think it was a technology that was worth developing?
Well, I think first misnomer is the word wind turbine, because in fact when we started, I think as you might have heard in the thing, we started working on wave energy. And this started back in the 1970s. And I first arrived, I got off the airplane in 1978 and joined the wave power group at the University of Edinburgh. And we started working on how to get energy from ocean waves. This was around about this time of the second energy crisis that most people who are old enough in this room might remember. That person pointing is Stephen Salter, and that is the original narrow tank in which he was testing his wave power device. But he began to realize that how was he going to get from low speed, high force, irregular ocean waves to a rotating shaft that could generate electricity. And this requires a transmission. Everybody's got a transmission in a car that they've driven here or been driven in. That's a transmission. But the transmission required for a wave energy device is far more difficult to accomplish. And so he thought about different means, including a spline pump. But basically, it was a very, very difficult problem. And all through the time that we were testing devices, we were trying to home in on technology that would allow us to make this important power transmission step. And making power transmissions is not intrinsically a very sexy thing. It's kind of like doing the digestive organs inside an animal. Nobody's going to remember you for it. So, but that was the problem. This is an artist's concept from 1978 or maybe 79 of the Salter duck, which he modestly calls it the Edinburgh duck. But you'll see a smaller tube in parallel with the bigger one, and inside that was a hydraulic power takeoff that was sitting in an evacuated chamber away from the salt water of the ocean. And that was all done with hydraulics. And in order to make that step to learn about hydraulics, it's quite complex, we got the help from a man called Robert Clerk. And the first video segment we're going to see is actually about, it's kind of a little homage to Robert. So maybe we could bring that one on now.
Anyone who enjoys watching diggers and bulldozers would guess that the best way to harness the hugely powerful undulations of a wave energy device, such as the duck, to the shaft of its electrical generator is by oil hydraulics. In fact, the hydraulic transmission for the duck called for a whole new generation of machines. When he arrived in our group, Robert Clerk had already spent much of his working life developing a remarkable axial piston swash plate machine. In the mid-1980s, Matthew Ree and Karen Gibson worked with him to build and test a 500 kilowatt prototype. Robert was uncompromising in his pursuit of high efficiency at full and part load, and we knew that such an approach was essential if wave-generated electricity was ever to be economically produced. The machine ran inside a dry case, and most of the bearings, including those of the swash plate, were hydrostatic. The outsides of the cylinder sleeves were pressurized to reduce piston leakage, and the tri-link connection eliminated slipper pads. The design incorporated hydraulic computing elements to optimize performance. Robert Clerk's brilliant synthesis of new ideas pushed the limits of conventional hydraulics.
Now that really was conventional hydraulics, which is what Robert brought to us. But the other half of that power transmission contained the seeds of digital displacement. And that will follow on, I think. Should I just carry on?
Yeah, carry on with that one, Stephen.
So basically, the low-speed part of what was involved with the duck was actually the precursor to digital displacement. We needed a way to have a very controllable transmission inside this wave power device. And Robert, although he came and helped us develop his own pump, which was incidentally about 4 times more power dense than the competing pumps at the time, he also gave us the background to start on this new pump. And I was involved really from the very beginning, at the age of about 23. I'll be 60 in January. It's been a long, long time. In any case, we started working on this new kind of hydraulics that we needed to develop in order to make hydraulics efficient enough. And so there's going to be a follow-on little bit of video now, which actually takes us through the early parts. And we're listening, by the way, to the voice of Jamie Taylor. Jamie was the first person I ever met in Edinburgh, and in a way belongs to the MacRobert Award as much as the other 5 people named. But we get his wonderful mellifluous Scottish accent taking us through this. So perhaps we can start that one.
To obtain the ultimate efficiency with a natural interface to electronic and computer control, Stephen Salter had already begun working with Robert, and now with Win Rampen, to develop a new technology, digital hydraulics. By using computer-triggered valves, individual cylinders of their new radial piston machine would be pressurized into circuit only when a work stroke was required. Individual units could be stacked on a common shaft to form the wedding cake machine, an energy processing system able to service many independent hydraulic circuits. This SolidWorks view shows the copper wire of the sectioned solenoid coils and the black valve poppets. Into each of the large diameter internal bores will be fitted a cylinder, like the one shown hatched in the centre of this Vascad drawing, the big end of its piston floated by hydrostatic pads over the rotor eccentric. The digital concept scaled easily to different sizes. The first machine was for a portable hydraulic power supply. The pump sits in the oil tank under the electric motor. Pressure and flow can be set by control knobs or by external command signals. This was the first machine built by Artemis Intelligent Power, set up by Win Rampen to commercialize digital hydraulics. Artemis supplied prototypes of the pump to Sauer Danfoss, world leaders in mobile hydraulics, and they continue to be involved with the work. Digital hydraulics required the evolution of a new species of poppet valve, which would rapidly change state following a current pulse in a solenoid. We made these low-pressure poppets from a carbon-filled thermoplastic called PEEK, polyether ether ketone. We'd already tested these little sample poppets to see if PEEK was up to the job. The rotor of the test rig subjected each of them to 1 billion pressure cycles and confirmed that PEEK poppets would be dimensionally stable, fast and quiet in operation. When the test rig was running, our colleague Ehsan was refining the design of annular poppet valves using computational fluid dynamics. By providing an inner and an outer flow passage, annular poppets will greatly increase valve flow capacities. This will be particularly important for larger machines. Meanwhile, spherical poppets are still useful in small machines. This recent SolidWorks model is for a new low-pressure poppet. The computer also generated the codes that Neil Caldwell fed into the numerically controlled mill. Neil is working with Artemis, and for his PhD, he's building a wheel motor. Up until now, the digital hydraulic machine has operated as a pump. is vital to extend its capability so that the same machine can also function as a motor. The first wheel motors will be fitted to a small vehicle, and the crucial test will be to generate zero-speed torque for startup. Neil also spent some time redesigning the solenoid magnetic circuits using the ANSYS finite element package. The solenoids are energized by brief pulses of current at precise times when the oil forces across the poppets are near zero. Magnetic forces are generally much smaller than the working pressures of oil hydraulics, so to have authority over residual fluid pressures, the solenoids must be very well designed indeed. On the prototype wheel motor, the valves and the solenoids are in place. The motor is enclosed in a cylindrical casing to completely immerse it in oil. There are a lot of variables to be optimised on its control card. The valve control algorithm and timings are particularly critical for motoring. Neil's using one of the original digital hydraulic power packs to drive the new motor. It's very handy for this kind of setup. Because there aren't any throttling valves, the oil and the machines stay cool. The gentle chatter of poppet firing also provides a kind of intuitive diagnostic tool. To our ears, the sound is like a kind of pleasing hydraulic dialogue between machines. The drive to develop intelligent hydraulics came from wave power research, but we now know that it will have a much wider impact.
Okay, well, if we move on then, Wynne, what have hydrostatic drives been used for before, and how did the digital displacement that you developed differ from it? What made it better than a mechanical or a direct drive for a wind turbine?
Neil's going to take on this
maybe
one.
I could take over from that point. I'm just going to say a few points about that previous video. Although it said in the voiceover it was sort of contemporaneous, it's actually quite old, which explains and excuses perhaps my hairstyles through the ages. The other point to make, the environment you see there was the wave power workshop as then, and essentially this is where Artemis was bootstrapped. It was not a salubrious environment. It wasn't an incubation centre with coffee machines and bean bags and all the other accoutrement today. It was a pretty down and dirty basement, but it had a very good machining workshop. It had three-phase power, and it had a ready supply of students coming through the door, keen to get some practical experience. It also had a lot of skips outside because the university at that point was throwing out all the equipment from their labs which were underused because they thought in the future everyone would just be doing stuff on computers. So as they were throwing out equipment, we were raking through these skips, finding electric motors and coders, all wonderful stuff. And so half of that stuff you see there was actually sort of built from scrap pieces.
Can I interrupt one more time? Our lab that you see there is now a coffee room with an espresso machine. And the other thing is Victrex Peak. They were the other finalists. We were using the materials 20 years ago, 20 more. Fantastic material.
That's worth saying, is that they have created a wonderful material which is unique in its properties, which actually enabled us to do some pretty unique things in turn. So, yeah.
With two MacRobert finalists synergistically working together to develop something that was successful.
Yeah. So, I mean, if I could try and answer the question now, you did ask, just to remind everybody, what had hydrostatic drives been used for before. So I can show that with this presentation here. I mean, you'll see these vehicles around in your daily life. The sort of rough and tough applications hydraulic power is used for. There's a rock crusher in the top left-hand corner, which is a very suitable job for hydraulic power. But basically, construction machinery, earth movers, and so on. And there's established industry around that to make the pumps which supply the fluid and the valves which control it. And make all of this machinery move. And it's a multi-billion-dollar industry worldwide. But it's worth noting the reasons why hydraulics has been so successful in some of these applications. One, it's very compact for its power, so very power dense. So typically, if you see a hydraulic pump matched to an equivalent electric motor as a paired setup, the hydraulic pump is much smaller than the electric motor. So they're very powerful for their size. They're also very tolerant of shocks. So the rock crusher is an excellent environment. And that's because the parts inside are loaded by pressure. And it means that you can limit the pressures inside with a valve, a relief valve. So that means that they're very good where the load is coming as shocks. You get a continuous control from hydraulics, so that forklift's a good example, going forwards and backwards all day, without gear shifts. And lastly, very crucial, you get very low cost compared with electric drives. So a lot of these applications you could do with electric machines, but it would be prohibitively expensive. So hydraulics still has a very good market for all of these applications, but there's some key downsides. Number one is poor energy efficiency. So believe it or not, a vehicle like that forklift with a conventional hydrostatic drive, it struggles to get an average efficiency over a duty cycle, averaged over the whole day of its operating, of better than 70%. So that means that only 70% of the energy that comes out of the engine makes it to the wheels. A large fraction of the energy ends up as heat in the oil, and then you have to pay to get rid of that heat. So that's a big downside which blocks application of hydraulics to many other fields. Second, high-frequency noise. You'll often hear these machines before you see them, and it's a trademark sort of whine that particularly these excavators and so on tend to make. And lastly, difficult to computer control. So these machines are essentially mechanical. They can be interfaced to computers, but the translation of the computer's command into the actual motion of the hydraulic actuators is rather tortuous, and it's fraught with difficulties, and it's not very direct. So the result of that is that hydraulic power can be seen as, in some ways, people see it as a dying industry. And in fact, we've heard leaders of hydraulics companies saying, my job is to manage the decline of this hydraulic industry, which is not very inspiring for the people that work for these companies. But of course, we think differently. And if there was a way of overcoming these three downsides, perhaps actually hydraulics could have a renaissance. So we introduce digital displacement. The animation here will be covered in more detail later on, so don't let it hypnotize you just yet, but we'll get to the operating principle forthwith. So it's called digital displacement, and the key principle is that we control the flow in and out of these working chambers with ultra-fast digital valves. I've actually got one here. This is of a very small machine suitable for a garden tractor, maybe it was 6 kilowatts or so. This machine is, this component's a poppet valve, which has a solenoid actuator inside it. And these are the electrical terminals of the solenoid actuator. And here's the controller of a digital displacement machine, which has the job of sending pulses to those valves at the right time, synchronized with the shaft rotation. So the mechanism is rather simple. It doesn't have to have a variable mechanism, which I'll show later. It has direct digital control. That means there's no analog conversion stages between the intention of the controller and the action of the machine. The machine is fundamentally digital, and it's not simply an analog machine that's had a digital layer sort of slapped onto it. Very important, it's scalable to multi-megawatt machines. So, of course, offshore wind these days at 7 megawatts, and really the future is to go to 10 megawatt and beyond. So to the traditional strengths of hydraulics, which we still have with digital displacement, finally we've broken through the three key barriers. So we've demonstrated efficiency as good as electric motors. So the machine, this part is from has efficiency of 97%, which is as good as electric motors. But the key thing is the efficiency at part load, which is I'll cover on the next slide. Second is a lack of high frequency noise. I will show you later a BMW, a video of a BMW demonstrator we made. And yeah, I'll tell you about my proudest moment in my engineering life so far. That's coming up. And then lastly, digital control built in. So as I said, there's no analog conversion mechanisms. It means the machine is an intelligent digital agent in a system, and it can both take commands and feed back its status to a master controller. So together that means that the technology is disruptive to the existing hydraulics market, but also it unlocks whole new markets for hydraulics. Drawing breath. So this slide quickly shows the difference between an analog machine and a digital machine. Analog machine on the left is controlled by varying the stroke, and the digital machine on the right by firing these valves in a digital sequence. Now, efficiency, this graph, just to point out the difference between digital displacement and conventional machines. In red is the conventional machines, in blue the digital displacement. You can see over a typical operating range, the digital machine is above 90% efficient, and the conventional hydraulic machine struggles to get to 70 or 80%. So it's really a dramatic improvement of energy efficiency. Briefly, the operating cycles of the machine. When there's no command or no demand from the system, the machine is idling. In that state, it's using very little energy, so it has very little parasitic load. These pistons and cylinders are simply reciprocating in oil, and there's very little in the way of friction or load inside the mechanism. When the command comes from the controller to fire a valve, then the solenoid valve is closed, like that, and that then causes the cylinder to be pressurized, and it does 1 unit of fluid displacement. So each time the controller makes a decision, 1 unit of fluid is displaced into the load or absorbed from the load. Hence, we deliver and absorb fluid in digital pulses. Some of the more details of the components will maybe better dealt with by looking at them after the talk on the table here. So as well as pumping, we can also do motoring, which is absorbing fluid from a source and turning that into shaft power. When you put the two of these together, you can have a pump on one shaft and a motor on the other, and you've made a transmission, as Wynne was saying, which is essentially a continuously variable gearbox to take mechanical power from one shaft to another. And lastly, although we have these digital control and we have a fixed number of cylinders, that doesn't mean that we have any sort of quantization or fixed number of set points. Essentially, we can mix the idle and the pumping strokes continuously and digitally in a binary sequence, and that gives us actually very linear and controllable output and a very fast response speed as well.
So why is that better then for a wind turbine, Wynne?
Well, wind turbines typically have the problem of matching the blade tip speed to the wind conditions, and that means the rotor has to go around at varying speed. But the grid likes to work at one frequency. It likes to be, in this country, 50 hertz. So you've got to have a transmission in a wind turbine and mostly generators like to work at high speed. So it tends to be a speed-up transmission, typically 100-to-1 ratio. But it can't just be a mechanical transmission by itself, because it also has to compensate for the variation in speed of the wind. So you typically have a gearbox in conjunction with a generator and power electronics that allow the generator to work to produce an output of 50 hertz. And that's the conventional defig unit that's been used on a lot of early wind turbines. And that essentially was our major competition. Got a lot of bad press because the gearboxes were proving quite unreliable. If you imagine these gearboxes, 100-to-1 ratio, all the teeth but 2 or 3 are having a holiday. The 2 or 3 that are under load are taking all the load and can be overloaded in that process because there's nothing to control or cap the load. So that has been somewhat displaced by direct drive, but direct drive tends to be heavy and have complex and expensive generators, and you still need the frequency converter stage. So the question you can ask yourself is, could we do the same thing with hydraulics? And if you do have a variable hydraulic transmission, that means you can use a fixed speed generator, and that's what the grid uses for virtually all applications. We call it a synchronous generator, and it gives us a great stability in the grid. So we get a bunch of advantages if we do things with hydraulics. We can reduce the weight and cost, because hydraulics inherently has fluid that's shared around all the different elements. We've got, for example, in the transmission you'll see presently, we have 34 pistons and cylinders working at the same time, all at the same pressure, and that pressure is capped by a pressure relief valve that stops the elements from getting overloaded, unlike the teeth in a gearbox. So we can reduce the size because we can reduce the overload capacity in order to make the component durable. It's tough for those same reasons. We're using the same components over and over again, and those components that are actually potentially wearing can actually be carried in your rucksack and replaced in situ, which is very, very important when you get to a scale like a wind turbine, when the wind turbine is actually very inaccessible, where you might want a helicopter on parts to replace something that's gone wrong. At the moment, it costs something like £1 million to change a gearbox in an offshore wind turbine. It's a very, very big bill.
So instead of a jack-up barge and a window in the weather, you can actually get a guy dropped with the material in his pocket to repair that which is...
That was the model. And Neil's got some of these components. These are actually faked up components. The real ones do exist, by the way. These ones are made of plastic. But the idea is that components like these would travel with the repair people. I guess continuing along the list, hydraulics highly controllable in this form, and we, as I said, we've got a synchronous generator. Now, before, I think it was insinuated that this was the first time that we, or suggested that the first time hydraulics was used for wind turbine. In fact, it was done a long time ago when, in 1977, a guy called Sir Henry Lawson Tancred in Yorkshire built a hydraulic wind turbine. You'll see that it wasn't God's gift to aesthetics. I actually happened upon this when I was about 22 years old, and I watched a man covered in oil with an adjustable spanner in each hand come out of the hole in the bottom of that thing. But this was 30 kilowatts, Europe's biggest wind generator in 1977, and Henry Lawson Tancred thought that this was the way forward. But we think it had three major problems that actually stopped it from proceeding. It had all the problems of conventional hydraulics in terms of efficiency. It used conventional hydraulics, which typically stop about 250 kilowatts, so it had a scalability issue. And just the way that conventional hydraulics work, it was very difficult to make it controllable.
So how did you get around these problems then and move along?
Well, that's digital displacement was the answer, and one of the people who isn't here tonight, one of the other winners, Stephen Salter, wrote this paper in 1984 about hydraulics for wind, and in it he prophesized and he basically described the transmission we've built all those years ago. So that's 31 years ago. All the different elements are essentially there. But he thought that we could go up to around, how many kilowatts? A 5-meter cam could absorb 30 megawatts. So he's got there's still some growth potential here, I think. But that was a very seminal paper, and Stephen is still working at the university coming up with interesting ideas. So that was maybe the beginning, and I think we got another slide here. That actually solved, conjecture, or at least in principle, solved all the problems that Sir Henry had come across, but it left us with one immediate problem. It was unproven. So we had to figure out how to prove it. In fact, it took us a lot of years before we finally could sit in front of you with this proven. So this, by the way, is what this migrated to into the circuit that we actually used in the 1.6 megawatt transmission that we built as a test one. You'll see more of this later. But you can see it's actually a very simple circuit with a pump being driven by the wind turbine and then a motor driving the generator with a few other components added on. So that's the pump, the motor, an accumulator which allows some storage of gusts and overloads. And this could be configured into a very compact and light format for a conventional wind turbine. This was actually modeled on a GE wind turbine, which we thought we could actually provide a retrofit for the braking gearboxes, and that's how it would have fitted into the actual machine. And I think that's...
So before you got... Oh,
those are the components. Sorry, those are a few of the components that we actually built as we moved on. But at this stage, it was very conceptual until we got some money from the Carbon Trust and started developing the components.
So you got the ideas, and you started to build elements of the system, but you were hitting one of the problems that often hits startups, which is financing and cash flow and how to continue and get confidence so that people will actually believe what you're trying to do and will actually start to make an investment. You know, a lot of people would have considered where you'd got to a still unproven technology. So how did you take things forward from those parts so that you could actually take it forward to sales and licensing to stay alive?
Well, I guess there's two different things that need to be addressed there. The first one is, do we want to go back and talk about the general licensing model, or do we want to stick on turbines?
Well, I think we're talking here about the overall business model of Artemis and how do you bootstrap a technology. So we did have a vision of a multi-megawatt machine. We knew it would take a lot of money to get there, to build such a machine, and we knew that we couldn't do that in one fell swoop. So we had to start small and start by targeting applications which were actually feasible for us with what the machines that we had at that time. So I suppose it gets us into talking to our licensees and trying to convince them that we could actually make something for a small machine.
Yeah, I think it's worth mentioning another person who entered in the picture, a guy called Waverley Cameron, who's still very much in our circuit of Artemis on the board. And Waverley said, well, you know, what you guys need to do is actually to get strategic investors from large companies, because that's the only way you're going to be able to move your technology forward. It's not really, he didn't like the idea of the conventional idea of venture capital. So, which I think in retrospect was very, very wise. And we had to kind of get ourselves into a position where we were attractive to companies that could use the technology in a commercial form. Mm-hmm. I think we're going to show the golf buggy video.
Yeah. So we had to demonstrate the technology in a form where an external investor could easily imagine it being applied in a commercially valuable application at the scale that we were at. So wind was totally out of reach, but what was in reach at this scale of a few kilowatts was a vehicle. So let's have a look at this video, which has got more embarrassing footage of my hairstyles through the ages. So yeah, this was essentially what we'd call a mule vehicle. That machine you saw me in the previous video going round and round, we packaged into a vehicle. So we have a pump on the engine and we have a motor driving the wheels. And on the tray at the front, we've got essentially the electronic guts of it laid out so that it was easy to probe and to fix if something went wrong. So it wasn't particularly well packaged, and it certainly wasn't ready to demonstrate to CEOs of big companies. But it was a feasibility study, and it was a proof of concept. We then refined that and actually simplified the system somewhat, and gave it a layer of computer control and a system controller, which allowed us to demonstrate some of the advantages for controllability. So here, for instance, I'm making the vehicle move gently. This is actually quite a challenge for hydrostatic transmissions. They often are a little bit jerky. So I had different modes of control. We could simulate electronically the drive behavior of the competition. So a conventional vehicle with a torque converter. We could also hear, what I'm doing here is turning this wheel. So this is a little electronic input which allows us to essentially wind the vehicle forwards and backwards. You can imagine if you're trying to get your car into your driveway or something, this could be quite useful to be able to sort of essentially wind it forwards and backwards and position it. But you can also have some serious applications, such as, you know, if you were trying to position a forklift. So that culminated in a demonstration. That is the chief executive of Sarah Danfoss, who got a ride on the golf buggy. By this time it had been cleaned up and I'd had a haircut, you notice. And it was really, that demonstration was one of the pivotal points in the Artemis story, because it gave a key strategic investor the confidence to fund us through the next stage of development.
Because you've called this skunk works, as part of your, ongoing development in terms of your ability to match what you were trying to develop with a variety of customers' different needs, so that they would actually pay you to take things forward.
I guess, do you want to talk about skunkworks, or is it me?
Yeah, I thought it was you, but
it's me, okay. Right, well, this is a picture from the air of Artemis in its current form. We actually spent 13 years at the university before they kicked us out, and we ran out of space almost simultaneously. But the reason to see this picture from the air is simply to realize that this is an enclosed space in which an awful lot of things happen. We have three different groups of people, and they interact all the time. Software, mechanical, electronics, and modeling people, all engineers, all working in the same room, and working on what amounts to a kind of continuous loop of development and test. And we don't see this as a process. Very often you'll see linear processes, start here, end up there. We realize that in order to make something really work well, you've got to keep going round and round the circle. I think James Dyson was alluding to this not very long ago in the media. But when you put all this in the same building, where all this capability is like this, it becomes like a skunk works. And lots of good things happen. You really start to understand your technology. You get total buy-in from your people. And you start developing new IP. So we've got something like 145 granted patents, 293 pending. But even more importantly, of the people in Artemis, we've got the inventorship really spread throughout the companies, 22 individual inventors with names on different patents. And that's the kind of brain trust that comes out of this. But a lot of this is all to do with not just people sitting at computers, but actually touching and feeling materials and understanding what can be done in an engineering context.
So you've basically kept control of the total technology package, all the way from the computer systems which control the system, to the machining and the manufacture of the valves, and the whole of the systems engineering that goes with it.
Yeah, we decided it was very important to make sure there was nothing strategic happening outside of the four walls of the company. Because, of course, that was a risk in terms of IP. It was also a risk in terms of our capability, that somebody could come and ask us to do something, and it would be, we would be essentially find out that we'd had a gap because we didn't know how to adjust that particular parameter. So we realized we had to have complete control of the core of our technology.
So,
yeah.
I was just going to say, so, I mean, you've got all the patents as you put on the slide there. So why did you not try to go for venture capital funding? Why did you decide that?
We did, actually. I made many trips to London to meet venture capitalists, but in the end, VCs are very interested in what their exit terms look like. And the development of technology like this takes a long time. It took 21 years till now, and I guess 17 years till we were acquired by Mitsubishi. So if we had put ourselves in the position where we were vulnerable to the exit terms specified in a VC contract, we would have been toast. Mm-hmm. And that happened to a number of our friends, actually.
And I went to California in 2010, about the time when we were looking to work out what route to go forward to commercialize. And I spoke to a number of VCs and realized that what they were looking for in California was an instantly scalable business. They wanted something that essentially could be copied and pasted, like software, for instance. So that's perfect for them. That's perfect for them because once you've got the code running, you just duplicate it instantly and with no cost. And what we had was a technology which needed a long gestation. It needed investment. It needed also an infrastructure of skills and facilities to support it. And it simply wasn't something that they could engage with. And I think that made me absolutely convinced the only way forward was through the acquisition by a major multinational engineering company.
Well, strategic investment worked for a good long time, but when we started working on wind, we realized we needed a lot more resource, and there were very few companies in the world that could provide that.
So you're going to talk to us about the journey to the acquisition by MHI.
Yeah. Just to explain further about what we do at Artemis, and we're designing machines, so of course we have to design the individual elements, like for instance the valves. We're writing software to make them all run, so this software that runs in here, it's a bit like an automotive control unit inside a car. We're building electronics to fire the valves, and we put all that together to make one machine, for instance a pump or a motor. We then have to think about how that machine is going to interact with the rest of the system, design some system controller using simulation, and then finally put all that together into a complete system comprising pump, the motor, and some sort of simulated environment, and do the complete demonstration. So that's the sort of activity that we do within those four walls. It's also important that we manage the risk through this process. Of course, you don't suddenly just design your valve and say expect it to work first time and order hundreds of them. You start off with a very unproven design, and what you're trying to do is funnel down to a single design which you can then mature through a number of tests and iterations until by the time it gets to what we call a D-class component, it's ready for production. In order to do that, we're doing a combination of simulation and testing. You start off at the element level, for instance, simulating the flow through the flow passages of these valves, and then work up towards a single working group. So that's where we would combine the valve and the piston cylinder and work on the dynamics of that one unit and make sure it could reach the performance we expect. Then you build a complete machine, and you have to simulate and predict how that machine is going to behave before you build it. And finally, a complete system, which again, simulation comes to the fore there. But that's all on paper, and that's all virtual. And nobody will believe it, and nobody should believe it until it's demonstrated. So what we have to do is replace all of these models with test rigs. So we start off on an element test rig. So that's, for instance, for a particular bearing on one of these parts. It's actually very similar to what Ricardo did in the early days of their engine research, where they made single-cylinder engines. You then have a working group test rig, which is just testing one module, essentially. You then build that up, in this case, to a 24-cylinder machine, combining those modules together. And then once that machine is rugged, you can then think about making a system such as this, which combines three machines together, all working in harmony. So in that process, you're essentially reducing risk of the components. But at each stage, when you combine components together to make a system, for instance, you're actually multiplying the risk. So we evolved quite a careful internal gate process to make sure that immature valves, for instance, didn't go any further and didn't get multiplied and be put into deployment, because then the system would have been unmanageably complex to work with. So we've learned this lesson the hard way, and that's one of our core philosophies. Yep.
So you got some investment from the Carbon Trust to start the, I guess it was the 1.6 megawatt turbine that you were driving towards?
We got a grant from Carbon Trust that was very, very helpful. They had an R&D sort of starter program at the time, which is unfortunately no longer, because they don't receive funding from the UK government any longer. And that allowed us to build the components for a 1.6 megawatt transmission, which was going to be the sort of scale of conventional wind turbines at the time.
At the moment, nobody wants to use hydraulics in wind turbines for the transmission because they would produce a lot less electricity per year. But by being able to match the efficiency of the mechanical gearbox, we can install hydraulics into the drivetrain. So we get all the benefits from the hydraulics, which are robustness, low weight, and also therefore low cost, without the disadvantage of the low efficiency, which is traditionally associated with hydraulic transmissions.
It gives us a much better performance because it's in the nature of a hydraulic or a hydrostatic transmission we use the word decouple. It sort of separates the two problems. The first problem is how you capture energy, the most energy from the rotor as it turns. And the second problem is how you turn the electrical generator at a higher speed and in the smoothest way. So you get the kind of, if we like, smoothest, the cleanest electricity coming out of it.
The wind drives the propeller, producing torque at its shaft. This drives a pump instead of a gearbox, produces fluid power, pressure and flow in a hydraulic circuit, which in turn drives a hydraulic motor whose displacement is smaller than the pump, so is able to drive the generator at a constant high speed. The whole system is continuously controlled and monitored by a computer.
Its roots came from work that we did in wave energy starting probably in the late 70s when we needed to find a way of conveying the energy from ocean waves, which are slow, irregular, have very high force, to the regular rotation of an electrical generator. And that, in fact, is very much parallel to what we're doing with the wind turbine.
What you have to imagine is that inside this machine here, there are many cylinders with pistons moving in them. And as the shaft goes around, we call it a ring cam because there's actually a cam inside there. So each time the shaft goes around, each of those 68 cylinders does a pumping stroke. With digital displacement, we can decide just when the pumping stroke is about to start pumping, we can say, well, do we actually want this to pump, or is it needed? Maybe we're working way down at part load at 10% of the full rating. If that's the case, then the computer will automatically disable that cylinder by controlling the valve at just the right moment. It just returns the flow, the oil, back to the low pressure reservoir. And we call that idling. And that's a really key part of it because a cylinder that's idling has got very, very low losses indeed. And that's a major contribution to the much higher part load efficiency.
We're releasing the part of the machine that you aren't needing at any one time, and in a way that it's not costing you much in terms of ongoing power consumption, whereas conventional hydraulics are spectacularly poor on that front, which is one reason that they haven't taken over all the different applications that they could have otherwise done.
This is a very large hydraulic motor, digital displacement. The idea is to have one of these pumps driven by the wind turbine rotor and driving two of these. Maybe the wind speed is only 6 or 7 meters per second, which is quite low for a wind turbine. We can turn one of these off. So we only have one generator, and that immediately reduces the losses even further.
It could, in principle, be applied at any area where you want to transmit shaft power. So we see that there are many applications beyond the wind turbine.
These include harnessing wave power, and Artemis has developed a car where the gearbox has been replaced with a hydraulic pump, which, via pipes, drives 2 independent hydraulic motors. It's shown around 50% savings in some circumstances.
With this carbon trust funded program, we've been able to go from a paper study, which people believed, industry being able to believe in, but couldn't really pick up from, to a real hardware demonstrator.
Because this has really shown the benefit of the investment and the grant from the Carbon Trust to be able to actually build a massive physical asset to demonstrate the technology to set you on the road. So given that you got to the 1.6 megawatt turbine, MHI were obviously seriously interested in what you guys were up to. So I think, Neil, you're going to take over the story from there, are you?
Yeah, so we were looking for a strategic investor, and at that point Mitsubishi Heavy Industries was also trying to work out what to do next for their journey in wind power. And they were looking for a technology which was scalable, which also played to their strengths, and which gave them a unique position in the market. In order to get to that point, we had to make a demonstration to them, and that Carbon Trust funding really set us on that trajectory. Once the acquisition was complete, we were set another challenge by Mitsubishi. So it wasn't simply that they acquired the company and then said, "That's great, I'm going to immediately adopt it for the next generation of our wind turbines." No, there were internal proofs that we had to make, and really around that, if we move on to the next video, we can have a look at the so-called Windrig 1. So this was at the scale of 1.6 megawatt. After the acquisition by Mitsubishi, we built this into a complete system demonstrator. And this was to show the efficiency, the controllability, the reliability at a scale which made sense and which could convince them to take the next level to scale it up yet further. You see some of the machines that we built in-house, and of course we're building the machines, we're building the electronics, we're also building the systems to test them. And you can see the importance of the craft skills as well at the heart of it. like any machine, they can fail because of the smallest detail, the smallest quality issues. So that it really is so important to getting to this point. So this test rig was quite a scary thing to operate, and there was a lot of pressure on it. We had teams of Mitsubishi engineers watching what we were doing, because of course they were going to make some very important decisions based on these test results. So this was another important milestone in our evolution towards the 7 megawatt goal. You can see on the wall there the electronics firing the valves. Each one of these little pulses represents one valve firing decision by the controller. And so that's the hydraulic dialogue between the pump and the motor is what's going on here in the controllers. What we're doing next is we're demonstrating the other side of the transmission, which is connecting to the electricity network through a synchronous generator. Very important there was to get the speed of the generator up and achieve synchronization as quickly as possible. So here we're accelerating and bringing the voltage into synchronicity in about 10 seconds. And that's much faster than any conventional technology could do. And in fact, that piece of work was done by a summer student who then went on to win an award for that as Student of the Year and also get his name on the patent. So it's the type of experience that students can have when they hit a really fast-moving development. You can also see there some of the modules being replaced, which shows some of those benefits too. So we could maybe just sort of move on now to show the next piece of video, which is showing what we did with Mitsubishi. Once the 1.6 megawatt had been demonstrated, we then had to scale it up to put it into a working wind turbine, because there were still some risks to do with what happens when you actually connect it to the wind turbine, and how does that whole system behave in all the different operating conditions of a wind turbine has to handle. So you can see here the scale is moving up. It certainly wasn't a manageable scale for Artemis. There was no way that we could have handled this type of project. Whereas this is exactly what Mitsubishi is so good at in this type of heavy engineering. So this type of testing was still working at the prototype level. These were still one-off machines, but of course they're one-off machines with, by now, a huge value. And so as the money increases, so does the stress and or another way of putting the excitement. So these control room, the atmosphere in these control rooms was sometimes pretty tense. It felt a bit like a rocket launch sometimes when we were gearing up to do the next power level up, so I will always remember that experience, that's for sure. So we can maybe carry on to the continuing our story and scaling up. Once we'd done the wind turbine at 2.4 scale, which was a resounding success, Mitsubishi committed to designing a 7 megawatt system, which we did as a cooperation. But of course, once it came to actually building the hardware, this capability is just incredible. Just the size of the cranes that are needed to move this stuff about are actually quite thin on the ground, these cranes. And the ability to have an integrated system with this weight of equipment assembled by a team of literally at some points hundreds, it was quite awe-inspiring to behold. And I remember turning up to help commission the system and just looking up at it and realizing it was the size of a 3-story house, and it contained equipment that we had only dreamed of a few years ago. So this is the digital motor being craned into position in the 7 megawatt, and you can see a view of from the front of the pump and the shaft. And then, of course, it wasn't just a prototype transmission. It was a complete wind turbine that involved the hub, the nacelle, the tower, and the blades, and all of that had to be developed by Mitsubishi as well. So it's a much bigger project even than the new transmission. We're ramping the power up. You can see the active power there in the green one, and many eyes scanning many instruments. The magical 7 megawatt, which was the target that we were aiming at, and there was definitely sort of a few cheers and pats in the back earned at that point, and a fantastic achievement by Mitsubishi. And we're going to carry on the story now to getting up to date and see how that nacelle, which is the sort of main working part, was actually turned into a working wind turbine at Hunterston, the west coast of Scotland. So this is a facility operated by SSE, and this build was actually groundbreaking in many ways. Just the crane operations broke UK records for the weight and height of the equipment that was lifted. And you can see some of the logistics involved. These parts had to be taken over in a barge from, and one of my favourite part of this is when the weight comes off, you can see the boat lifting up. So this type of coordinated ballet, essentially at Artemis, we were just watching this from the sidelines. In fact, we had a video monitor in our office, and we could see it from Edinburgh, and we were just watching in awe as this ballet of assembly took place in front of our eyes, with this beautiful backdrop of the west coast of Scotland as well. It's easy to lose track of the scale, but when you see the size of the people, let alone the aerial work platforms that are scurrying about, you can get an impression. The overall diameter of the turbine is 167 meters, and it's.
That's a rival turbine behind it, by the way.
It's only 6 megawatts.
It's smaller.
Yeah. Yeah, so this was essentially the record-breaking lift that led to the finally getting its nacelle put on top of the tower. And of course, you know, the wind turbine assembly is such a complex operation. Everything has to be planned down to the last minute, and it's really an area where we had to step back. Obvious health and safety, literally step back, obvious health and safety issues, and everything had to be planned down to the last element. And you have the blades going on. They're using something called the blade dragon, which is a special clamp to position the blades at just the right angle. And this goes on like that. You can see this video has been speeded up somewhat. Yeah.
And all done within a weather window, presumably.
All done within a weather window. That's a very good point. Yeah, our Japanese colleagues can be somewhat superstitious about that. And one of them is convinced that he is the stormy guy, because whenever he turns up, it gets stormy. So he's got that reputation. So finally, it's been assembled and it's been commissioned and it's working well. It's doing exactly what it was expected to do. And it's led to the next stage, which is the world's largest floating offshore wind turbine. This is positioned in the Sea of Japan off Fukushima, and has now been commissioned. It's working. It's just about to be connected to the grid, and really is a hugely high-profile project within Japan, and is a symbol of Japan's step towards renewable energy.
So tremendous success story, Neil, which you must be very proud. But you employ 50 people, 50 plus people, and at the time of the acquisition, many of them would have had shares in Artemis, because that's the way you ran it. Since the company's still there and you're still here, you clearly didn't all clear off to the beach in the Caribbean. But what difference did it make to them, and what difference has Mitsubishi's ownership meant to you as a company?
Yeah, I mean, I think that maybe Wynne should talk about the shares, because it was really one of his ideas.
At the beginning, we decided that we couldn't pay massive salaries to our young employees. We thought to attract people of quality of Neil and all the other people that came aboard, we would have to think of something else, and so we thought giving people some ownership in the company would be appropriate. And as it turned out, that was a very good thing to do, and it was even a very small share ownership really motivated people to take part in the company and take ownership of the company, in the sense of taking ownership of problems as they arose, and really helped us all row in the same direction when things got tough or whatever. And I think that would be certainly my advice to anybody starting a small company, that they should think of doing the same thing.
Yeah, And yeah, post-acquisition, I think what we've realized is that we're connected to a company which has so many capabilities that the sky really is the limit. And so we've really teamed up with MHI, and you can see Artemis there, and our capabilities dwarfed really by Mitsubishi's capabilities and the sheer number of, and breadth of skills that they have. And so we really had to form one team, an international team, to achieve this project. And I think what's come over very strongly is the depth of a company like Mitsubishi's culture around making things. They call it in Mitsubishi monozukuri, the art, the science, the craft of making things. So it's a culture which celebrates the skills and the crafts of the people that make stuff as much as it does the more scientific aspects. And no more than any other company, perhaps Mitsubishi knows that one single bad weld can sink a ship or cause a power station boiler to burst. So that means they have an extraordinary focus on skills and on developing those skills. They're very proud, for instance, of their entrance in the Skills Olympics, which is something perhaps we should reflect on as a country, whether we perhaps are paying enough attention to the Skills Olympics or compared to the Sports Olympics. So we've teamed up with Mitsubishi, and really what Mitsubishi have been able to do, I don't want to compare our achievement with that of Frank Whittle, but you can see what he had in 1941, a pretty rough and ready machine, and not ready to go in a plane. And here we are in 2015, taking them for granted. Well, what Mitsubishi inherited from us essentially in 2011 was an equivalent level, a proof of concept demonstrator. And what they've done in 4 years is scaled it up and turned it into a fully working machine. And it's just an incredible capability to watch. And we could reflect on the history of Mitsubishi as well. It was actually founded by a Scot, Thomas Glover, who really kick-started the Japanese Meiji Industrial Revolution. And he was from Aberdeenshire. And in the early days of the 20th century, there was many pieces of equipment going from Scotland to Japan, including that giant cantilever crane from my hometown in Glasgow, one of which is still working in Nagasaki and still being used by Mitsubishi Heavy Industries to move heavy equipment. And the one in Glasgow is, I think, is a tourist attraction, sadly. So here we are in 2015, and Mitsubishi are making the turbine and essentially exporting it back to the UK. And it's worth contemplating what we're maybe perhaps missing in the UK compared with what they have in Japan. I mean, imagine that you want to make an industrialized society. You probably want to start with some metal, so you'll need machinery to make the metals. You'll need, once you've made the metal, you need to cut them in different shapes, so you'll need machine tools. Now you've got your parts, you probably need to move them around, so you'll need forklift trucks. Once you've got your parts, you might want to build those parts into an engine, for instance. So there's an engine from a ship. You've got your engine, you might as well build a ship now, so you might as well build that, and that's an LNG carrier that's going to carry fuel to another thing you're going to build, which is a power station to burn the fuel. And then all these people that work on all this stuff, they're all going to need to get around, so you're probably going to need some people movers and trains, and they might have to go on some business trips, so you might well need to build them an aeroplane. And then to coordinate all this, you'll need some satellites and communications, so you're going to need one of these to launch them into space. So those are all products made by Mitsubishi Heavy Industries, and this is what gives Japan such a strength in engineering. And it's worth reflecting on whether the conventional wisdom in Britain might be that if you have an advanced economy, you have to move away from those sort of perhaps dirty occupations of engineering and into the so-called knowledge-based economy. Well, all of these items of equipment are full of knowledge, but they're also full of craft, and I think it's something we have to take to heart and aim for as a country.
Thanks for that, Neil. I mean, I think probably what we're going to do is open up the questions from the audience in a minute, but before I do that, what difference has winning the MacRobert Award made to you, and what did MHI think of it when you did?
I think the most amazing thing was just the reception that it got in Japan, because I think it was an experiment for the Japanese to buy us, and the fact that we have got this exceptional result has really made the people running Mitsubishi aware of the fact that they actually are working with people that they thought they wanted to work with. So I think it has really raised our profile in Japan, which is very, very helpful to Artemis. And of course, I think the day after we won, the day we got back to our desk after winning the award, we were visited by somebody in a helicopter. He was that impressed. So yeah, it has really changed our horizons.
Yeah, the way I would put it is it's like the red carpet rolls in front of you wherever you go, because there's so much recognition, and you know, essentially you've got over the first hurdle because they already believe that the technology is working and that you've achieved something significant. So it's been a huge benefit to us. Yeah.
Well, thank you for that. So if we can ask the audience if they've got any questions that haven't already been answered, if you can stand up and, or when you take the mic, please say your name. If we can try Dave first, then Dougal.
Hi, Dave Delpy. I'm currently chair of DSAC, but in fact I've just joined the judging panel for next year's MacRobert Prize. Can I ask a question about the one bit that you haven't described? You've described a lot of really interesting mechanical components and digital components and software, but nowhere have you mentioned the working fluid, the hydraulic fluid. And I would have thought in optimizing a hydraulically based machine, the characteristics of the fluid would be something that you would also look at, but it's not been mentioned at all.
Well, I think the reason that it doesn't get mentioned is it's one of those, it's sort of like in the hydraulics industry, there are very standard fluids, and the minute you want to deviate from those, then flags go up. So we have what are called iso oils, and they're basically mineral oils. And the minute you want to use something else, you're in trouble, because it's either very expensive or very exotic or very something. The aerospace industry has to use special oils because of the very low temperatures and for flammability reasons. But generally speaking, they are very standard. Artemis is fairly oil benign, or we're undemanding because of the very robust pumping group we have isn't demanding any particular characteristics of the oil. So we don't really care. We take what oil comes at us. Oil, by the way, has some really good advantages over something like water. Water has very low viscosity and is a very poor lubricant. Oil is very slippery, as you know, if you've stepped on it on the floor.
Yeah, the way where exotic oils come into play is you've got a very large temperature range, and certainly if you're going to make a vehicle that's going to run over from winter to summer, then a synthetic oil or it can be very helpful for that. But yeah, as Wynne says, it's been a part of our story, but we've never wanted to stick out because we want a special oil, because that would mean that people would discount what we were doing, because basically what happens in the field when that excavator doesn't have any oil in it, whatever is around gets put in, and that's what's going to happen. So you can put whatever sticker you want on the tank, but that's not what's going to go in.
I should say one thing. We have made a pump that worked on water as well, so it's not very fluid specific.
Thanks, Dougal. I think you had something.
Hi, I'm Dougal Goodman from the Foundation for Science and Technology. Fascinating talk. I remember a long time ago talking to you about the BMW and the motors, and you emphasized to me the enormous saving in fuel that resulted from using the hydraulic system. Why have you not concentrated on the auto market rather than the offshore wind market?
Could be a good time to show that video, actually, because we've got one queued up. If we
a
could
video
maybe,
that we prepared earlier, just for you.
We could maybe play that one. Yeah. And yeah, we should say some of the background to this. So at the time when we made this BMW, the technology was exclusively licensed to a major industrial company, and that actually took away some of our ability to chart the course through the strategy. In other words, they told us what we could do, and we didn't tell them. This BMW was a demonstrator for us to try and show in a very demanding application, a luxury vehicle, that we could meet the highest specifications in terms of efficiency, noise, controllability. We packaged it all up into the same space as a conventional vehicle, and it did show tremendous benefits, especially in stop-start driving. So you can see here in this video, we're driving around Artemis, and this little graphic in the bottom right-hand corner is showing the state of charge of the accumulator. Accumulator is like a sort of physical battery. It stores energy in the form of compressed gas. And compared with a conventional electric battery, it doesn't store an awful lot of energy, but you can get the energy in and out very quickly. And so that means that for stop-start driving, particularly for heavier vehicles, it's actually a very suitable way of storing the kinetic energy of the vehicle and getting it to the wheels. You can also see there the engine speed, which is shown in RPM, is continuously variable. So we could actually optimize the operating point of the engine because the transmission didn't have a fixed number of gears. So we made that demonstration. At that point, we were simultaneously developing wind. And it's fair to say that we made the call that wind was going to be the thing that took us to the next level because there was such demand there. There was actually quite a lot of competition in the hybrid vehicle area, particularly passenger car hybrids from electric. And I almost told you about my proudest moment, but it was we took that vehicle to BMW's Munich test labs, and we were doing everything very carefully. And one of their directors of NVH, noise, vibration and harshness, he came bowling in and says, "I want to drive that car." And he grabbed the keys and we went out onto the streets of Munich, and I was doing that because we'd never driven it in traffic before, and he just drove it around Munich and we said, "It's not insured," and he said, "Don't worry, we own this town." So that was reassuring. And at the end of his drive, it was my proudest moment. He just turned to me and he said, "Nicht schlecht," which is German for not bad. So I thought, well, if the head of NVH of BMW thinks it's not bad, then we've done a good job. But so we couldn't control necessarily what happened next because of our licensing agreements. Since then, we've actually wrested some of that control back, and we're now working on heavy vehicles, which is where electric hybrids are the weakest, and where hydraulic hybrids definitely have the major strengths. So we've demonstrated a bus, and in fact we've got a video here we could watch if we want to just segue straight into it.
Final video.
Final video.
Artemis is an engineering company. It's a research and development company, and we're developing a strange and exciting kind of hydraulic transmission technology.
It's a team of young engineers that believe in the technology and that want to bring it to the market.
Artemis is a spin-out company. It came out of the University of Edinburgh, and it came out of one of the hardest problems of all in engineering.
Digital displacement technology is a new type of hydraulic machine. We have combined the very robust aspects of hydraulic machines with modern control technology. Each piston is individually controlled with a solenoid-operated valve, which is controlled by the microprocessor. This allows us not only to get very fast response and accurate control over the machine, but also allows us to achieve very good efficiencies.
We're developing it as both an OEM and a retrofit project. Throughout the project, we were considering the ease of installation as quite a high priority. So it's very straightforward to install and doesn't require a huge amount of skill in terms of the operator.
In contrast to conventional hydraulic machines that are typically based on axial piston arrangements, what we can see here is that we have a better efficiency at times of full displacement. So for example, when we have full load braking or acceleration. So for any hybrid technology to be adopted by the main market, It's very important that we can create payback on the fuel saving on its own. So this system here has a potential to save around 20% of the fuel. And because of this very low cost that's possible for the system, we can achieve payback times that are well within the periods that operators would expect, typically 2 to 4 years.
Where the challenges of storing kinetic energy are so extreme.
No, that's great. So, I mean, hopefully we'll have given you a bit of a taste there for the things that are still in the pipeline for Artemis to continue to grow success. Before coming back into the audience, I've just got something I want to explore with you about skills base and the STEM initiatives, the way to encourage young people into engineering. Of course, the Academy's got a number of programs where it's trying very hard on a national basis to try and up the image of engineering, completely change public perception, following its University of Engineering report, and also to work with the other professional institutions in doing things. What's your experience in Edinburgh and elsewhere about the attraction of engineering and the sort of work that you do to the young people that you come across?
Well, I think both Neil and I have been involved in this in different ways, but I think Uwe, who you've seen on the screen quite a lot this evening, is the most fantastic motivator and enthusiast. At the moment, he's enthusing and motivating the third-year mechanical engineering students at the University of Edinburgh, which is already too late. But just before we started this, we were talking about this primary
engineer.
You want to talk about that?
Yeah, so I mean, I've just heard about an initiative to try and teach kids at young age, primary age, about engineering and to give them some insight into what it's like to be an engineer. Certainly, the primary engineer, secondary engineer sound like great initiatives. I mean, my experience was coming through schooling that I wasn't actually sure what an engineer was, and certainly if you watch the BBC, you think the engineers fly in to fix down pylons, and that's basically what they do, isn't it? Engineers fix the pylons, and it's actually, I think, an ongoing struggle to make sure that engineers get the recognition that they deserve for basically enabling our modern world. But it's also, there's so much missed opportunity, I think, to enthuse kids about making things. I think engineering as a profession has tended to want to distance itself from the craft elements or let's say the maintenance man who comes to fix your boiler by emphasizing all the brain work, the simulation and so on. But in actual, to get engagement from younger people particularly, making something is what is so hardwired to be satisfying. And you learn with your hands as much as you learn with your head. And so I think the most powerful thing we could do is give every kid the opportunity to make something and get that satisfaction, whether it's from a Raspberry Pi or building a model aircraft or a drone or something along those lines. And that enthusing is still necessary as you go through to tertiary education. Sadly, many of my fellow students at Edinburgh University went on to join the City of London in so-called financial engineering rather than contributing to our economy in another way. And I think maybe now the universities are starting to realise, and certainly the students are starting to demand, to get access to exactly the type of stimulation that we had in Artemis, that they were so desperate to experience.
Well, I mean, I think we'd all agree with you there, Neil. I mean, that's something that came out of the recommendations in the University of Engineering report about the importance of the practical aspects of the higher education system, as well as much lower down the chain into primary schools. But I think before we close, we've got somebody desperate to ask a question there as well.
Zuhair Hanna, retired mechanical engineer. Is it feasible to replace the plunger pump by another types of pump like screw pumps or gear pumps to get better efficiency, mechanical efficiency?
Yes, but typically other forms of pump, piston pumps are used usually in high pressure situations where people are interested in working at relatively high system pressures. The other forms of pump tend not to work at those pressures, so you end up with circuits that are designed to work under slightly different circumstances. But if you want to redesign them, you can make a much more efficient system generally by using piston pumps. It tends to cost a bit more, but then when you look at the energy usage through the year, if some of these things are used very consistently, then the difference in cost pays itself back very, very quickly.
Thank you. Perhaps one final question from me. Well, there's two questions from me in that case then, before I ask the last one. It's about the innovation landscape in the UK, Neil, where things are changing. They've changed last week as a result of the Chancellor's announcements in the CSR about moving from grants to loans in innovation space and other things. Is there anything that you would wish to change of the system that is there currently?
In a word, no. I think Innovate UK is actually the jewel of the crown. It's a beacon for the rest of the world of how to fund innovation. That is combining research and commercial interest. So this sort of match funding model. Certainly, we think it's a very pro-organisation. We think they have a very good bunch of people supervising the projects. And I think there's a lot of, we've got something that really has to be taken care of there and make sure that we don't break it by changing to a different model of governance.
Sure. And I mean, are there other things? Because the Academy has got initiatives like its Enterprise Hub, which seeks to bring young entrepreneurs into contact with world-class engineers who can offer advice and help them on their journey. I mean, is that the sort of thing that you would have benefited from, or that you yourselves would be interested in participating in?
I benefited very much at the very early days of Artemis. There was all sorts of the sort of standard growth things that were on offer, but none of those were really appropriate for Artemis. But there were two individuals, one of whom unfortunately died. He was a respectable age, but unfortunately died a couple months ago. And he really helped me see how to start Artemis, and with very little resource, and introduced us to the appropriate people, which ultimately led to the right business model, which ultimately led to our success. This was not a get-rich-quick scheme, I should add.
Yeah, that's right. Okay, so we're going to close out tonight by looking again at the Artemis team. Yep. And they've got a very interesting multinational team. One of the stories that we heard as MacRobert judges when we went round was that Uwe, the chief engineer that you saw on a number of occasions on the video, he got on a bus from Germany as a postgrad student and came to Scotland to ask for a job because he'd been so impressed by the paper that had been written by Stephen Salter and in Edinburgh University, and he stuck around for the last 20-odd years.
That's right. I mean, we do have this team, but it started off very small, especially three people and a dog in a shed at the University of Edinburgh. And this early picture is from those days, the early 90s, developing the first digital displacement motor.
Let's pump that one.
Wynn's still got that jumper. And then
true story. Yeah.
We move on to the phase of sort of organic growth. We were still under the wing of the university, and we were sort of mixed up with the Wave Power group and the culture there, which was of making your own prototypes, and nobody who was designing something shouldn't also make it. So what I had to do was design the thing, make it, and get it working. And I think that we've stuck with that philosophy, and so we still have a very practical culture. So we've grown the company in the image of the technology, so to speak, because we've needed a mixture of skills. We also need a mixture of personalities. So as we've grown, it's becoming really apparent that you can't run a business if everybody's a fizzing ball of energy running around having ideas left and right and centre. You need the yin and the yang. So, for instance, two of the other winners of the MacRobert, Uwe, you could say, is the yin because he's so full of energy and full of always starting new projects. And on the other hand, we've got Yang of Pierre, his opposite number in the mechanical engineering team, who's focusing us on the details, who's making sure that nothing gets lost, and keeps us looking at quality and also reporting back to Mitsubishi. So you need those different types of characters to make a complete functioning team. We tend to have a very flat structure. We don't have a great hierarchy, and basically we don't have job demarcations either. So if there's a pool of oil on the floor, the managing director is meant to stop whatever he's doing and mop it up right then and there.
Lead from the front.
And lead from the front. So long may that continue. One of the great things of the Mitsubishi acquisition is that they didn't mess with the magic. We've seen many other examples of companies that have taken over and just swept away the existing culture in the board, and they've been left with a pile of dust at the end of it because everybody leaves. But actually, Mitsubishi were very careful to make sure that Artemis was kept as this sort of our ideas factory. And it was actually one of their real strategic thoughts was, don't turn it into another bit of Mitsubishi, but its function is actually to fertilize Mitsubishi, if you like, with new ideas. So we really appreciate that and hope it will continue.
Well, thank you very much indeed, Neil and Wynne, for talking with me tonight, and also bringing your wares to share, and the video clips and the slides that you've shown us. I hope you've all enjoyed the In Conversation. As I said, it's the first time we've tried this sort of format, so we'd be very interested in your feedback as to whether you liked it or not. And Wynne and Neil will be around to talk with you downstairs as we have the reception in the National Grid in the David Sainsbury's rooms. So if you'd like to adjourn there and chat further, then that will be absolutely fantastic. So thank you very much.